if you have V is equal to U direct sum W, and both the U and the W are both L modules, both L submodules of V, all right? Then we say V is the direct sum of the L module U and the L module W. And the module V is said to be indecomposable if this is impossible. All right, so if no such U and W exist, then V is indecomposable. If there are no non-zero submodules U and W such that that is true. All right. Clearly an irreducible module is indecomposable. All right, so irreducible implies indecomposable. However, the reverse implication, not always true. All right? And we'll give an example of that in just a minute, okay? He says the L module V is completely reducible if it can be written as the direct sum of irreducible modules. Thank you. So if you have V is equal to S1, direct sum S2, direct sum direct sum SK, where S sub I irreducible for all I equals 1, 2, k, then this is said to be completely reducible. All right, completely reducible. All right. Check on my phone. Make sure I don't have a. Okay, I'm fine. Why is my computer kabinging? What's it complaining about?
Probably an email.
Maybe. Maybe. All right, we good. So example. Oops. If you have F a field, and you look at the algebra of diagonal example 1, L equal to the diagonal n by n matrices over the field. All right, this is a subalgebra of GLNF. Okay, great. He says, in this case, Fn is completely reducible. So here, Lx on the natural module here is just n Fn, right? And what are the irreducible submodules here, Audric? I think you could figure it out, So
diagonal matrices.
Yeah. Like. Well, no. The question is, what subspace of the n by n column vectors? Can you? What are It's complete. Well, not. We can have zero vector, but we want non-zero subspaces, right? That are irreducible. What's it? Yeah, the base exactly. So you just let S1 be the span of E1, S2, span of E2, and so forth. Right? Sj, span of Ej, you know? And so V Fn is then the direct sum of S1 and S2 and Sn. So it is completely reducible, all right? Completely reducible because these are all one-dimensional, right? Hence, since they're one-dimensional, they're irreducible, right? So there you go. The diagonal, the sub-Lie algebra of diagonal matrices is completely reducible into a direct sum of one-dimensional irreducible representations. And he has an advertisement here as this being a reinterpretation of a previous result. I mean, here, the SI are the weight spaces for L. And as we can view this as a reformulation of example 5.2 in chapter 5. And then his next example is the triangular matrices, right? Over field. And again, you can use the natural module Fn. And he claims that this is indecomposable. And I think we've already done the heavy lifting today to see that. Oh, maybe not. See exercise 7.6 below. Note, however, provided n is greater than or equal to 2, V is not irreducible, since the span of E1 is a non-trivial submodule, so V is not completely reducible. See, exercise 7.6 below. Where did that go to? Below where? Where is exercise? Oh, it's later. It's on page 63. It's just to prove that that actually is what he claims. Fine. All right, it's indecomposable. What does that mean? What is he claiming? That you can't write it as a sum of two L submodules, right? I mean, we proved that the V sub R was a submodule of L, right? Earlier today, we did that. I don't know. I mean, to understand this, I have to see that every submodule of L has to have that kind of form or something like that. Well, this is a claim. All right, this is a homework exercise. The bottom line is this is a homework exercise. It's not, I mean, this is an example, but it's not easy to, I mean, it's not immediately obvious why this is true, okay? This requires some calculation. So let's go on. All right, so that brings us to section 7.6, which is on homomorphisms. Homomorphisms. Let me move you. Hey, get down there. Are we good? Maybe.
Yeah.
And let's see here. So we have, the question is, what is an L module homomorphism or Lie homomorphism? So In this case, we have two L modules, one V and one W. Now W is not necessarily a subspace of V, right? Now W and V are two separate vector spaces. They're both L modules. A L module homomorphism from V to W is linear map theta from V to W such that what? Probably it preserves the Lie algebra action, right? So theta of x dot V, indeedly doodly, is equal to x dot theta of V, just what you'd expect for all V and V and X and L. All right, great. What's an isomorphism? Well, it's a bijective L module homomorphism. All right. And, oh, neat. Suppose you've got a representation phi sub V that is a mapping from L to GLV, right? And you have a representation phi sub W from L into GLW. All right? Then in the language of representations, how does the L module homomorphism connect these two?
The composition well, the compositions send V to W, sort of.
Sort of.
It sends something. Theta sends theta sends things to W, but phi sends things from W to GLW. So you can go in between GLW and V by composition of maps.
Yeah. So he writes it this way. He says theta composed with phi V is equal to phi W composed with theta, I think.
Yeah, because in theta you land in W, and then phi sends it from, wait. Phi W doesn't input, W sends stuff.
Let's see here. If I draw a picture, I don't know where I want to draw the picture. I'm not sure what the right picture is to draw here, honestly.
Well, they don't input the same things. You just take V composed with theta.
Well,
Like theta will use something in W.
okay, so
W takes something in L. Oh, L is the submodule.
well, L is the Lie algebra here, but
Yeah.
all right. So okay, so if I feed this x, right, I have theta of phi of V of x, right? Then that is an element of what? Well, phi V of, well, first of all, I can't even do that. That doesn't even make sense, I don't think, because phi V of x is an element of GLV, right?
GLV, yeah.
So I should let this act on, like, you know, little v. Then this would be an element of, this would be an element of V, and then this becomes an element of W, because theta takes me from V to W. On the flip side of things, if I do theta, phi sub W of, golly, this is very sneaky what's meant by that formula. this is a little bit sneaky what's meant by that formula, because I mean, because it means this. Well, anyway. I'm not sure I'm going to say anything terribly intelligent at the moment about that. But this brings us to the theorem, 711. And this, and here it's basically the isomorphism theorems for this world, right? In particular, if you have, you know, theta as there, right, then the kernel of theta is an L submodule of V. And the image of theta is L submodule of W. And there's an isomorphism, namely that V mod the kernel of this is isomorphic to the image. And then there's also analogs of the second and the third isomorphism theorems for the factor module and the factor of the factor module. All right. Let's see here, let me look at this example. Let L be the one-dimensional abelian Lie algebra spanned by, say, X. We may define a representation of L on a vector space V by mapping X to any element of GLV. Let W be another vector space. The representations of L corresponding to linear maps F and G are isomorphic if and only if there's a vector space isomorphism. Blah, 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 blah. Well, we may need to come back to the idea of example 7.12 as we work on more specific things next chapter. So we'll save it for then. Let's see here. And then finally, we have one more section here, which is Schur's lemma. So probably the example 7.12 I just skipped over, that probably actually matters for calculations in the next chapter, okay? That may actually matter. So section 7.7, which is Schur's lemma. What's it say? It says one of the best ways to understand the structure of a module for a Lie algebra is to look at the homomorphism between it and its other modules. It's natural to begin looking at homomorphisms between irreducible modules. Let's see here. Suppose S and T are irreducible Lie modules, and that you have a non-zero module homomorphism. So if we have S and T are irreducible Lie modules, right? And you actually did have a, you know, this is pretty obvious actually. So suppose you have, you know, irreducible. What's the problem with this? Can you have a Lie suppose you have a non-zero module homomorphism. What does that immediately give you by the first isomorphism theorem of the previous section?
That the kernel's empty?
Well, it gives you, I mean, you got submodules, right?
Yeah.
So you've got kernel, submodule of S, and you got image right? Submodule.
Yeah, wait. I thought you said it was irreducible.
I did.
Irreducible.
I did. I say, suppose you, so this is the discussion. Suppose you have a L module homomorphism between irreducible L modules.
Yeah.
What is this force upon us? Well, that means that the kernel of theta has to be 0.
Okay.
Or it has to be, so the kernel of theta has to be either 0 or all of S. And the image of theta has to be either 0 or all of T, right? So it's either the 0 map or it's a what?
The whole thing.
Yeah, so let's see, what does he say? It follows that theta is an so it follows that theta is an isomorphism from S to T. So there are no non-zero homomorphisms between non-isomorphic irreducible modules. So when you have two irreducible modules, they're either isomorphic or the only homomorphisms between them are the 0 homomorphism. That's the totality of this discussion, okay? Either when you have two irreducible L modules, either they're isomorphic or they're not. And if they're not isomorphic, then the only homomorphism from one to the other is the stupid zero morphism. You know, so in other words, there's no non-zero homomorphisms, as he says. He says, now we consider the homomorphism from an irreducible module to itself. From an irreducible module to itself. All right. And this is the namesake of this section. This is Schur's lemma. It says let L be complex Lie algebra and S a finite dimensional irreducible L module. All right. A map theta from S to S is an L module homomorphism if and only if theta is equal to lambda times the identity on S. In other words, it has to be a scalar multiple of the identity transformation on S. This is Schur's lemma. All right, are we good so far? Let's look at he says, let's look at the proof of this. He says the if direction should be clear. Is it clear? In other words,
Let's see, we have finite dimensional irreducible map theta, and theta is a homomorphism. So, like, yes, no. Like, if I thought about it like matrices, like I could understand that, like, you know, you can only have the one, the identity times the scalar, but that doesn't quite
Let's see.
Take the question.
We've got a complex Lie algebra. S is a finite dimensional irreducible L module. And L module homomorphism. Well, it's, let's see here. Let's see here. Well, it's irreducible. It's irreducible. So that means that the homomorphism has to be a isomorphism, right? Right?
Yes.
Because the only, I mean, there are no non-trivial homomorphisms. There are no non-trivial homomorphisms from this is, I mean, this was for S and, I mean, is any L module isomorphic to itself? Yes, right?
Yeah.
So that forces the homomorphism to in fact be an isomorphism. So if we have an L module homomorphism is necessarily that theta is isomorphism. So it's an isomorphism from S to S, right? And it's not just, it's a Lie algebra isomorphism from S to S, right? So what do we know then? I guess I erased it, but we have conditions, right? Like theta. Well, I think if we use the definition of, Lie algebra isomorphism, golly, well, it's finite dimensional, right? So you can pick a basis for S as well, right?
Yeah.
And I mean, of course, it's not the case that any isomorphism from a vector space to itself is a scalar multiple of the identity, right? We've got lots of isomorphisms from a finite dimensional vector space to itself, which are not scalar multiples of the identity, right? Because GLN is full of such matrices. So it must have to do with the Lie algebra homomorphism aspect of this, like that. How's it go? Goodness gracious, Audric, I'm blanking here. I erased it. I erased what I need to write down. I guess I just have to look back. So we have that theta of x dot v, right, is equal to x dot theta of v, and that's for all v and s in this context and x and L. I think they're trying to get me to leave the room. Let's see here. What remains. Well, anyway, I'll tell you what, Audric, I'll come back to this hopefully next class, all right? What remains here, though, let me just finish up the concept. Next, the application here is let L be a complex Lie algebra, V an irreducible L module. If you have Z in the center of the algebra, then Zx by scalar multiplication on V. That is, there is some lambda such that Z dot V is lambda V. And the proof is like 3 lines, which we should look at next time again. Corollary to the previous lemma is that simple modules for an abelian Lie algebra over C are one-dimensional. All right, we'll explain that as well. All right, remark. In chapters 5 and 6, we worked with the hypothesis that a Lie algebra was a subalgebra of GLV for some vector space V. In other words, we're assuming that L had a faithful representation on V. Although we shall not prove it in this book, it is a theorem, Adou's theorem or Adou's theorem, that every Lie algebra has a faithful representation. So in particular, what Adou's theorem says is that you can choose a subset of like GLV. You can basically embed any Lie algebra as a matrix Lie algebra if you, take a sufficiently large dimension. And he says if L is a Lie algebra and phi from L to GLV is a representation, not necessarily faithful, we can apply the results of chapters 5 and 6 to the subalgebra image of phi under a subset of GLV. In particular, it makes sense to talk about weights and weight spaces for L. So I think that is a foreshadowing of things to come. And then hopefully so I'm hoping to finish up the Schur's lemma next time very briefly, and then we will go on to chapter 8. Woohoo! So, and then Cartine's criteria. So anyway, we'll just keep soldiering on here and see where we get to. So sorry I didn't get a little bit further, but again, I think the cleaning people are trying to get in this room and they're distracting me. Sorry about that. Sorry about that.
No. I also didn't do my notes beforehand, so it's a little less than optimized.
Well.
And it's not as smart as they usually do.
Let's see here.